Okay, now, good afternoon, everyone. Now, this part here that we are doing is the gas turbine power cycle. Okay, closed gas turbine unit and open gas turbine unit, work examples 1. So, in this work example here, stated in the question, a gas turbine unit has a pressure ratio of 10 to 1. Has a pressure ratio of 10 to 1. So, what is this overall pressure ratio means? So, we have to refer to the TS diagram. So when you refer to this TS diagram here, you can see the points of 1, 4, and 4 prime is actually at one pressure line. And the other points such as 2, 2 prime, and 3, they are at another pressure line. So when the question say overall pressure ratio or pressure ratio, that means it is referring to this pressure line, the pressure here, to this pressure here is 10 times. So that means this pressure on any point on this pressure line here is 10 times the pressure of any points here on this line. So if let's say the pressure on this line 0.4, 0.4, and 0.1 is having a pressure of 1.01 bar, then 0.2, 2 prime, and 3 would have a pressure of how much? If it is 10 times. So it is 10.1 bar. So 10 times of 1.01, okay? 10 times of 1.01. So a pressure ratio of 10 to 1. So if let's say, for example, we refer to any of these formulas here, P2 to P1, so you can take that is 10 to 1. So it is 10 here basically, okay? And I have explained to you earlier that when you refer to this diagram here, actually you have to split it into A part, A section, and gas part, okay, for any open gas turbine unit. For a closed gas turbine unit, then you will have the same system or the same working fluid flow throughout the whole entire system, the cycle. But then here, since we have this component here called the combustion chamber, so what happened in the combustion chamber actually, chemical reactions takes place. So if you have A going in, then you will have hot gas coming out. So, and that is because why? The exit here or the outlet here, you cannot send it back to point 1 to the compressor to run on the further cycle or further up the cycle. Okay, so that is why it is open. And this hot gas here usually is exhaust or discharge to the atmospheric air. The intake is atmospheric air. Discharge is also atmospheric air. So actually this is not advisable because it's some sort of like giving air pollution, or it actually creates global warming effect. So which is actually no good. So usually we take this outlet here and when we bring it to another component that is just, let's say for example, a steam power plant to heat up the water before it goes into the boiler. Okay, the purpose is to save up the fuel. So a gas turbine unit has a pressure ratio of 10 to 1 and a maximum cycle temperature of 700 degrees C. Isentropic efficiency for compressor and turbine is 0.82, 82%, and 85% for the turbine, 82% for the compressor, 85% for the turbine, respectively. Calculate the power output. So power output usually is taken as mass flow rate times network out. I think I have already taught you in the previous lesson, okay, in your podcast or your PowerPoint presentation. Okay, electric generator geared to the turbine when the air enters the compressor here. It enters here. So at 15 degrees C, and the rate, the mass flow rate of air into this is actually 15 kg per second. Okay, so you can take this 15 plus 273, so it's 288 Kelvin. 700 plus 273, so you have 973 Kelvin, the maximum temperature and the minimum temperature. What about the pressure? So since this is atmospheric air, do you know what is atmospheric pressure? Atmospheric pressure should be around 1.01 bar. So 1 atmospheric is actually refers to 1.01325 bar, or you can just simplify it or make it as 1.01 bar going in here. okay, if you were to consider so. But otherwise, you just leave as pressure ratio. Now take the CP, that is the specific capacity at constant pressure for A. This is the A side. Remember, this is the A side. Look at my PowerPoint laser pointer. Okay, so this is the A side, blue, and the red color is the gas side. And this is your shaft. Okay, this is your shaft that is connecting compressor to turbine, gas turbine, and to the generator, or you can say this is a propeller or an alternator or whatsoever. Then the gamma for A is 1.4. These two values are actually standard values. And then the compression for the compression process, that means the A side. And then the CPG for the gas is 1.11. And the gamma, the adiabatic index for gas is 1.333. That is given in the question. Now, sometimes they ask you to consider CPA throughout and gamma A 1.4 throughout. That means if it is throughout, that means if they give you only one CP and one gamma, that means it is A working throughout the entire cycle. Then that should be a closed gas turbine unit and a closed constant pressure cycle. So here, that is the TS diagram. So you note here, this is 700 degrees C. You have to add it with 273, so get 973 Kelvin. Okay, and then this is the lowest temperature, the inlet temperature or the intake temperature of 15 plus 273, so you have 288 Kelvin. And then you have the isentropic efficiency for both sides, the compressor and the turbine. Now you see for this section here, I have listed out two formulas, two different formulas. One is for the isentropic efficiency for the compressor, and the isentropic, actually this formula is referring to the temperature pressure relationship. So remember this gamma here, bear in mind, this gamma here, you should use gamma for A, because this should be 1 to 2 is looking at, the 1 to 2 is actually referring to the A side. Okay, the 1 to 2 is referring to the A side, and the 3 to 4 is actually referring to the gas side. Okay, so from this, okay, now this is the isentropic efficiency for compressor. As I've said, okay, you take the, this is the theoretical work input. Okay, you can see the CPA is not here anymore. The theoretical work input, and this is the actual input. So the isentropic efficiency for compressor is actually defined as the theoretical work input over the actual work input, as where you can see the numerator. This is the numerator, this is the denominator. And if you want to get something that is less than 1, make sure your numerator is much more lesser than your denominator. That is from this point to this point here, which shows you the irreversibilities. Irreversibilities because it's shown as dashed line. 1 to 2 here is solid line, that is perfect isentropic. So if the question say perfect isentropic, you don't have this 1 to 2 prime, this line here, you have to erase it off. And this line also, you have to erase it off. If they say perfect isentropic or isentropic efficiency 100% for the compressor and turbine. So this line 3 to 4 prime and 1 to 2 prime should be erased off. Okay, so now that is this. So they have given us the isentropic efficiency for compressor 0.82. So, and we know that, okay, T2 prime, T2 and T1 we have already known that is 288 Kelvin. T2 can be found by using this formula. Now, please look here. Now, look at my laser pointer. This formula here can only be used for this line here, 1 to 2, which is a vertical line, a straight vertical line here that shows isentropic. So this formula can only be used for 1 to 2, not 1 to 2 prime here. And also can only be used for 3 to 4, this line, not this dashed line here. This is irreversible. This is also irreversible process. So no. So 3 to 4 is the turbine side. So this is the isentropic expansion. 3 to 4, that means you refer to this vertical line here. And bear in mind this gamma is G now. It's the gas side. So it should be 1.333. Okay, and then this pressure ratio 3 to 4, you should know that is 10 to 1. And this is also 10 to 1. So there will be no problem finding out T2. So once you got T2, T1, and the isentropic efficiency for compressor, you will be able to find out T2 prime. And the same as for this, the turbine isentropic efficiency is given 0.85 or 85%. T3 is 973 Kelvin. Okay, how to find out T4? To find T4 prime, you must have T4. So T3, you know, pressure ratio is 10 to 1. Gamma is 1.333. So you can find out your T4. Once you got your T4, you can find out your T4 prime. So everything is shown here on my workings. Look at my laser pointer. So that is your T2. And from this part, you can find out your T2 prime. And based on the turbine side, remember this gamma G here should be 1.333. 1.333. So you got this. Okay. So then you got your T4. Once you got your T4, put into the isentropic efficiency for turbine, find out your T4 prime. Why do we need T2 prime and T4 prime? Why do we need T2 prime and T4 prime? So the work input now is actually based on this. CPA, T2 prime minus T1. It's no longer T2 minus T1 as you have in your constant pressure cycle. And then your work output should be CPG. This is CPA. That is CPG. T3 minus T4 prime. And your heat supply should be CPG. T3 minus T2 prime. So that is your heat supply. Okay, so everything is shown here. So once you got your T4 prime, you can find out your work in. Okay, and then you can find out your work out. You can find out your work out. You can find out your work input, then your network output. Now, what is this mechanical efficiency? So that is to show the efficient, how efficient is the power shaft in transmitting power from one component to another component. Now, most of the time, the mechanical efficiency is less than 100%. Why? Because of frictional loss between the shaft transmission thing, okay, from one component to another component. So once you take into frictional loss, then you have a mechanical efficiency that is less than 100%. So, but then in this case, the question has not given us any mechanical efficiency. So that is why I assume that's 100%. So that is 1. So always then only you have to work network out. Network out, that means is the net energy that you receive. Okay, this is your gross work output. This is your actually your work output only. This is work input only. So once you take work out minus work in, actually you have already got your net work out. But since there's a loss due to power transmission, to shaft transmission or shafting, okay, so you have to include mechanical efficiency, then only you can get your net actual value. So that is your net work out. So once you got your network out, multiplied by the mass flow rate that is given in the question, then you will be able to find out your power net. Okay, so that's all for this section. Thank you very much. If you find the notes is useful, please subscribe and like. Okay, thank you very much.